All right, so in this video, we're going to tackle the topic of orbital hybridization. And really, this is about the fact that our theory of molecular geometry doesn't really jive with our theory of orbital geometry. And so we need to revise our model, so to speak. The first example we'll look at is the Lewis structure of methane. And we have learned that methane is a tetrahedral molecule with 109.5-degree bond angles. And experiments show this is indeed the case. It's a nonpolar molecule. However, if we think about the geometry of orbitals that we learned that since carbon, that central atom, has electron configuration 1s2, 2s2, 2p2. Let's just look at the valence electrons, 2s2, 2p2. Then that doesn't really match what we observe in the molecule methane, because those 2p electrons, or those electrons in the 2p orbitals, remember the p orbitals, there are 3 of them, and they're all oriented 90 degrees to each other, or 180 degrees to each other. How could that possibly account for electrons being shared at 109-degree bond angles from that central atom? And that angle is observed in carbon in all sorts of compounds called alkanes. So the electrons must be doing something other than this. P orbitals are arranged at 90 degrees, but carbon molecules show bonds arranged at 109. Well, in order to resolve this discrepancy, a theory was developed that those atomic orbitals must hybridize and become what we call molecular orbitals. So we assume that those carbon atoms have the potential to form different types of orbitals for their electrons, and those orbitals must be arranged tetrahedrally. Hybridization, of course, is mixing two things together to get something completely new. The mixing of the native atomic orbitals, in this case, to form special orbitals for bonding, or bonding orbitals. And there's a couple of different types of hybridization that we want to be familiar with in our class. The first is what we'd call sp3 hybridization. And I want to make clear that that superscript 3 has nothing to do with the superscripts that we're used to seeing in electron configurations. When I write 1s2, 2s2, 2p3, or 2p2 or 2p4, we're talking about the number of electrons in a particular orbital. When we write sp3 hybridization, we mean that is a hybrid that is made from 1s and 3p's, and hence sp3. It has nothing to do with the number of electrons, but rather the number of orbitals. Here's a graphic which I think will help. For instance, here you can see that in the atomic orbital, to begin with, on the left, we have a 2s and we have 3 2p's. Now, in the hybridized orbital that we're suggesting in this theory, they have all been combined to form 4 orbitals of equal energy. They're all called sp3 orbitals. Why sp3 orbitals? Because each one of those has resulted from blending together 1s and 3p's. So here we have 4 orbitals of equal energy value. And they would be, as we combine 1s and 3p, equivalent and therefore arranged tetrahedrally. They all have the same amount of energy, and those 4 orbitals are identical in shape. Here's what they look like. It looks like a little mushroom from Mario, so think about it as a 1-up, right? Here's what we started with, 1s and 3 different p's. But they got put in the blender, blended up together, and then they came out as 4 separate orbitals of equal energy. And if you imagine all of those superimposed on each other, centered around the nucleus of the carbon atom, then you can see what we get here, the tetrahedral arrangement of electron pairs. There it is, all shown together to account for the geometry in methane. 4 sp3 orbitals. Now, we're going to continue our discussion to other molecules and talk about other types of hybridization. But this would be a good time to pause and review the first type of hybridization, if necessary, sp3 hybridization. Let's talk about another molecule when we expand our discussion to other types of hybridization. The other molecule we're going to look at is the ethene molecule, or ethylene, and that's C2H4. And you can see there's a double bond between the two carbon atoms. Well, we learned that this is a trigonal planar geometry around each carbon. Those are 120-degree bond angles, and that's indeed what's observed in nature. But this does not match with our understanding of atomic orbitals. Once again, sp3 hybridization also couldn't account for the ethylene molecule because sp3 hybridization was what accounted for 109.5-degree bond angles, tetrahedral bond angles. So there must be something else going on in a carbon atom to give us 120-degree bond angles. Again, we're going to assume that the atomic orbitals in the carbon atom in this case have hybridized to form different special orbitals for bonding, in this case sp2 hybridization. In other words, an s has hybridized with only 2 of the p orbitals, and that means one of the p orbitals has not been involved in the hybridization process. We call it sp2 because it's the hybridization from an s and 2 p orbitals. Here they are to begin with, an s and all 3 p orbitals, but only 3 of those have actually been hybridized. This one was not invited to the party, right? This one was left out, and it's going to be an interesting fact to consider later that there's an unhybridized p orbital here. But the 1, 2, 3 that were hybridized give us 3 orbitals, hybrid orbitals of equal energy. Each of them are going to be arranged trigonal planar arrangement because they all have equal energy. And one of those p orbitals is not used. It's going to be oriented perpendicular to the plane of the sp orbital. So here's some pictures that show that. The picture I want to show actually is a model that I'm going to show underneath a document camera here. And the model is showing our sp2 hybridization. And you can see I've got the double bond in the middle here. And I've got a trigonal planar geometry. This is one of the sp2 orbitals. This is another sp2 orbital. This is another sp2 orbital. But if you remember, there's also an unhybridized p orbital, which we're going to show as being oriented perpendicular to this plane. So let me add the pieces that complete this model. And you can see that the unhybridized p orbitals are actually going to give us that double bond. So here's again the sp2 orbitals, and here you can see delocalized both above and below the central axis between the atoms are what we call the pi bond, which is formed from the unhybridized p orbitals. And you might think that this looks like a triple bond, and I don't blame you, but really what we're showing here is a second bond. Both the pink and blue here are representing that second bond. The first bond is what we call the sigma bond, and it's directly between the 2 carbon atoms, right on that central axis. But the pi bond is delocalized both above and below the central axis, and that is the second bond. So this is a double bond that's shown in this model, not a triple bond. And that's because that second bond, which we call the pi bond, is actually formed from these unhybridized p orbitals. So sp2 hybridization is the first time we're going to want to make this distinction between sigma bonds and pi bonds. Sigma bonds are going to always be on that line running between the 2 atoms' nuclei. So that central line that we'd think of, and that is going to be the result of electrons in hybrid orbitals, hybridized orbitals, the sp2 orbital in this case. But the pi bond is going to be the double bond in the case we just showed. And it's going to also apply when we talk about triple bonds in a moment, but you'll notice that it is in the space above and below the sigma bond. So here's the sigma bond. The pi bond is going to result from electrons being shared in these unhybridized p orbitals, which exist in the plane perpendicular to the trigonal planar hybridized orbitals. So here's another great picture that shows how we started with 1s and 2p orbitals, and we put them in the blender, and they came out as 3 hybrid orbitals of equal energy. And when we put those all superimposed on each other, centered around the nucleus of the atom, you can see you get electron clouds that are trigonal planar in arrangement. And those 3 electron clouds are the 3 hybridized sp2 orbitals. The unhybridized p orbital that was not invited to this party is not shown, but it is the one that's involved in the pi bond. So here's another image which tries to show what I show you underneath the document camera a minute ago. There's the sigma bond, here's the pi bond, and here's everything together. When we draw a Lewis structure, we draw 2 bonds to show, or 2 lines to show the double bond. One of those is a sigma bond, and the other is a pi bond. So this is a good image to study and look at and think about the concepts for. I'll move on now to talk about the last scenario we'll consider, which is a triple bond and what we call sp hybridization. In this example, we'll consider the Lewis structure for carbon dioxide. And you can see that carbon dioxide is a linear molecule, according to what we learned, with a 180-degree bond angle, and that's true. That's what carbon dioxide exists as in nature. But again, that contradicts our understanding of atomic orbitals in carbon, and neither sp3 nor sp2 hybridization can account for this, because sp3 accounts for tetrahedral geometry and sp2 accounts for trigonal planar geometry. So we're going to invoke another theory of orbital hybridization, sp hybridization, to explain linear geometry. And linear geometry is what we have here with 2 double bonds. It'll also be what we have when we have a single and a triple bond around a central atom. sp hybridization is so named because it's just going to involve hybridizing an s orbital and a p orbital. That means the other 2 p orbitals are left out. If we just combine one s and one p, then we get 2 sp orbitals of equal energy, and they're going to be arranged in a linear geometry. The 2 unhybridized p orbitals that were not invited to the party are going to be involved in forming pi bonds, in this case 2 pi bonds. Here's this image again showing how we started with an s and 3 p's in the carbon atom to begin with, but when we hybridize them, 2 of these, let's say this one and this one, have been hybridized to form these new unique orbitals, but the other 2 p orbitals were not hybridized. Here's another helpful image. We put these 2 in the blender, and these are the hybrid orbitals we get out. There were 2 p orbitals not included, but the 2 hybrid orbitals that are formed, shown here superimposed on each other, centered around the nucleus of the atom, we get 120-degree bond angles between these 2 electron clouds. Now this is going to be a more complicated image to represent, and I'm going to show you underneath the document camera first. There's a model that we have here which shows the molecule we were just talking about, which is acetylene. And also that's known as ethine. And you can see, first of all, in the middle here, I've got the sigma bond. This is the center showing that sp orbital hybridization, sp hybridized orbital. However, we also have above that center, you can see the unhybridized p orbitals are forming a pi bond, and below the unhybridized p orbitals are forming a pi bond. And so you can see that there's this delocalization. In other words, it's away from the local center of the molecule, and that's where the double and triple bonds really exist. So if we have a triple bond, that means we have 1 sigma and 2 pi bonds. In the case of carbon dioxide, we didn't have a triple bond, we had 2 double bonds, but we can still account for this in this model. There's a sigma bond between this carbon and this oxygen, and there's 2 pi bonds, one of them on the x-axis, and over here on the z-axis we have the other pi bond. So here's a sigma bond between carbon and oxygen, and the pi bond is delocalized above and below that sigma bond. Now, we can consider other types of hybridization called sp3d and sp3d2. However, because there is evidence to suggest that these models are inaccurate or may be incomplete, we're not going to include them in our curriculum. And the College Board has decided not to include these expanded octet um, molecular geometry theories. So while you might see a few of them come up in OWL occasionally, we never really need to worry about d orbital hybridization. Although it should make sense, if we have 5 domains around the central atom, then another orbital must have been involved, not just the s and the 3 p's, but a d as well. And if we have 6 domains, then it must be 2 d orbitals as well as all the others which were involved. You don't need to worry about naming the orbital hybridization in an expanded octet. We do need to know about those geometries, but we don't need to name the hybridization. So here's a good practice problem to look at. I'm going to pause the video here, and I'm also going to come back to discuss the summary of all of the geometries we looked at and how the hybridization models that we just discussed fit in. If we're talking about SP hybridization, that could be a scenario like this, where we have a triple bond and a single bond, or it could be a scenario like this, where we have 2 double bonds, or it could even be a scenario like this, where there is a lone pair. In other words, we are talking about the number of domains. In any of these cases, we could talk about the central atom here as having sp hybridization. If it's sp2 hybridization, there's a couple of scenarios. We're talking about a trigonal planar molecule, and it could be this arrangement, or it could be an arrangement like this, where one of them is a lone pair. It could even be a double bond with 2 lone pairs. But in each of these cases, we have roughly 120-degree angles between bonding domains, and we always have 1 sigma and 1 pi bond that are involved. In this case, there's 1, 2, 3 sigmas and 1 pi. In this case, there's 2 sigma bonds and 1 pi. But if there's a double bond, one of those is a sigma bond and the other is a pi bond. If we're talking about sp3 hybridization, it could be any of these scenarios. However, it's just electron domains that we're looking at. If there are 4 domains, it's sp3 hybridized. If there are 3 domains, then it's sp2 hybridized. And if there are 2 domains, then it's sp hybridized. This also correlates to bond angles, roughly 180, roughly 120, and roughly 109.5. And we'll deviate from those ideal bond angles, of course, more when there's lone pairs or when the peripheral atoms here are different from each other. But that's another helpful way to summarize how hybridization is related to electron domain geometry.